Welcome to the SEI Podcast Series, a production of the Carnegie Mellon University Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the U.S. Department of Defense. A transcript of today's podcast is posted on the SEI website at sei.cmu.edu/podcasts.
Welcome to the SEI Podcast Series. Today we're talking with David Svoboda and Joseph Sible, who are both engineers in CERT's Applied Systems Group. Dave and Joe are our primary developers and maintainers of the SEI CERT Secure Coding Standard. Today, we're going to hear about proposed changes to this standard, specifically in the area of risk assessment. And I'm Bob Schiela, the Deputy Technical Director of Cybersecurity Foundations in the CERT division here at the Software Engineering Institute. Welcome, Dave and Joe.
Hi, Bob. It's good to be here.
Thanks, Bob. It's great to have you. So, Dave and Joe, you've both been guests on previous podcasts in the area exploring software security, for example, in the Rust programming language. For our viewers and our listeners who've not seen or heard those podcasts, I'd like you to provide a little background information and about who you are and how did you get into secure coding research?
Well, Bob, I started with CERT about 15 years ago, and when I had started, I had experience as a research programmer working with C, C++, and Java, so I had a pretty good sense of the capabilities, the good points and the flaws of these three languages.
Sure.
So adding more languages like Rust, I come to it from a language lawyer perspective, more of a Stradivarius perspective of how is this language put together rather than a Paganini language. How do you play it?
Right. And I know you have originally a degree in computer science. You're coming from the computer science perspective.
Right, that too.
Right. How about you, Joe?
So I got a little bit of a later start than Dave did. I've been with CERT for coming up on 8 years. It was around 2020 that I started maintaining the coding standards in earnest. My main focus has been on the C language with a little bit on the C++ standard.
Sure. And as at least recently, there's been a lot of attention in C and C++, the memory safety of those languages and other languages that are more memory safe. So let's give a brief overview of the secure coding standards, remediation costs and the proposed changes, how the metric was initially measured, and why now is it outdated.
So remediation cost is measuring how much manual work is required to find and fix violations of some rule. So it's right now a number between 1 and 3, and it comes out of two different categories of whether the rule is automatically detectable or not, and whether it's automatically repairable or not.
Right.
So today, before I go there, I'm going to explain the concepts of detectable and repairable, the way we use them.
Okay.
Detectable isn't just there's some tool that says it can detect this thing. It can be reliably detected with a low false positive and false negative rate.
Okay.
Repairable only qualifies if it can be fixed locally, so say not changing a function's definition in all of its call sites, just its body, and that it doesn't have the risk of breaking properly working code.
Okay.
And in practice, that means unless it was undefined behavior before, the existing behavior has to be preserved.
Okay. So the standards as a whole are a good resource for learning about secure coding and how to secure code. With respect to the remediation cost, one of the values of the coding standard is that it also helps with priorities of finding and fixing weaknesses and flaws in code. And so I think what you're talking about with detection is how tools or what methods might be able to detect. And then similarly, as the technology is advanced, how tools and methods can fix or automatically fix the some of the flaws. And so it's helpful with regard to picking and choosing and prioritizing which ones, which weaknesses and flaws you might address. Is that correct?
That's right, Bob. Specifically, each rule has a, the risk assessment basically produces a composite number that we call priority, and the remediation cost factors into the priority, with the argument that rules with a higher priority should be fixed and addressed before rules with lower priorities.
Right.
So a static analysis alert that's automatically detectable will have a higher resulting priority than a rule that's not automatically detectable. And likewise, a alert that's automatically repairable should have a higher, should be attended to before a rule that's not automatically repairable.
Right. And for those that use static analysis tools, they probably know there's a common problem of so many, too many alerts and findings for an organization or a team to actually address. And so the prioritization becomes important for helping to decide where to put your attention to fix those. And so that's where the risk assessment as a whole can help, and remediation costs coming back down to part of that. So I was hoping you could walk us through your approach and efforts to updating the standard for the remediation cost.
So the change we're basically making is, as more and more tools are capable of doing automated repair, we don't want to gate repair behind detection anymore and having an effect on the score.
Mm-hmm.
So today, if an alert's not automatically detectable, it automatically gets the highest value of 3, whether or not it's automatically repairable. But now that there are repairs that, even if the detection was a false positive, so we don't want to call it automatically detectable, it's still worth doing the repair because it doesn't hurt anything if it's a false positive. And if it is a true positive, it'll fix the problem.
Right.
So to add to that, we discovered this during a 2-year project that we put together called Redemption. Initially stood for redemption of false positives, because the argument was that we would repair alerts even if they were false positives, with the argument being that repairing a false positive is harmless to the code. For example, a null pointer, if you have a null pointer in line 10, you could spend hours trying to figure out if that's a true positive or a false positive, or you could just simply add a null check on line 10 and fix the problem, which takes 5 minutes. It'll take longer to test, but the actual coding repair can be done automatically. It's easier to repair the alert than it is to try and determine if it's a true positive or not.
Right. So that gets to how different the method and measuring the findability of a weakness is from its ability to fixing a particular weakness.
Exactly.
Sure. So at the same time, though, you also are rolling out or considering these changes. And one thing I don't think we mentioned much is whenever you're transitioning for a change, you need to somehow support legacy or minimize how it might impact previous metrics or uses of the metric, and have some way to convert to the new metric. And so can you talk a little bit about that change of the new way and how that might impact people using in the past?
Sure. So as engineers, we like building systems. We like making things better. And, well, at first we wanted to rush ahead and make this change. But this change of updating remediation costs to about 100 CERT-C rules, that's the total number we've got, making those changes might break some tools that depend on it. For example, the Parasoft tool provides nice, nifty reports about your compliance, how your code base complies with the CERT-C standard, and it heavily integrates our risk assessment, remediation costs, and everything else.
Right.
So if we change how the remediation cost is computed, that requires some work on the part of the Parasoft developers. And so we don't want to make this change without alerting them that, hey, we'd like to make this change. What cost does this impose on you? We want to make sure that the change is handled smoothly by Parasoft and by everyone else who are depending on our coding standards.
Right, because there are many different types of users that use the coding standards, whether it's the coders or tool developers that are trying to to map to the secure coding standard, and so we need to consider all of those different roles and
Changing
perspectives.
changing the remediation cost will also change the priorities because the priorities are computed, and that means some rules go up in priority, others go down, and this will affect, most people who use our coding standards for auditing code, and it also includes static analysis tool vendors like Parasoft.
Right. So again, with respect to the new way to measure remediation costs compared to the old, can you outline how you've tested and evaluated the new metric and its impact on how people are using the standard for their code for secure coding?
Right. So at first, this was a solution that was strictly in my head, and I thought, I'll just roll this out. No one will really complain about it, right? And it's not that way. I decided that what we should do is pick a handful of rules, and we wound up picking the integer rules. I think there's 7 rules. They are int 30-c through to int 36-c.
So those are all related to integer types of weaknesses or problems that might cause insecurity in code.
Right, such as avoiding integer overflows, avoiding division by 0, that kind of thing.
Mm-hmm.
And we simply said, here's the old metrics, old remediation costs. Now, given our new system, what would be the new remediation costs? Do any of them change from the old? And what I realized is, what we tried doing is we did an exercise where it was you, Joe, and me, and did we have someone else? I think Caden?
Yeah, we had Caden on board.
Right. So each of the 3 of us tried to figure out what would be the new remediation cost for these rules. How should they be changed?
Mm-hmm.
And what we discovered is that we all had 7 different metrics. I thought this one would be high, and Joe thought it would be medium, and Caden thought it would be low.
Okay.
So that just simply meant that we needed to be more precise about the definitions.
Sure.
And it also meant that it was very prudent of me not to rush ahead and make this change without at least without being a lot more careful and involving Joe and Caden in it. They're both smart guys, and they both pointed out. Well, they both helped me discover what was unclear or how we interpreted the definitions differently.
Right. Because you each had a different perspective, so there was some ambiguity that you wanted to make more precise.
Exactly. So at this point, we came to an agreement about what the remediation cost should be, and we streamlined the definitions so that we all had consensus. And now that at least we have consensus between the 3 of us, we want to bring this new method to everyone else to see if there's any other problems or difficulties with consensus. Is that does the consensus only apply to the 3 of us, or does it apply to you and everyone else as well?
Right. So have you had any chance to evaluate the impact of the new metric and how this new metric with respect to adding the fixability perspective will be used either by tool developers or by tool vendors or by developers with respect to this new dimension that you've added to the metric?
So my previous boss always said that the goal of the SCI and the goal of our work with the DoD was to address the DoD's pain points. What problems do they have that are really painful for them to work with? And one of the pain points, as we've already talked about, was the deluge of alerts. They get far too many alerts to deal with.
Mm-hmm.
Now, this is definitely true, but I have experienced this pain point very personally because I've done a whole bunch of audits of DoD code, and that means that I have to deal with the deluge of alerts. I've had code bases with hundreds of thousands of alerts to deal with.
Right.
And of course, I can only look at maybe 2,000 of them, and I have to leave 98,000 unexamined.
Yeah, it's just overwhelming. And actually, I know that sampling and selecting which ones to evaluate is a whole different topic. But yeah, so go on.
So first of all, our redemption project was partially designed to help deal with this deluge of alerts by automatically repairing alerts so that the 100,000 alerts comes out to a much smaller number, like hopefully 30 or 40,000. But as that's the redemption, as far as the CERT standards go, we would like for the remediation cost to help with addressing that deluge of alerts. So, for example, an alert that is automatically repairable, you don't need to audit that alert. You can just use the automatic repair tool. You can use a tool to repair the alert automatically, and therefore you don't need to audit it. If an alert is not automatically repairable, but it is automatically detectable, then, as Joe said, that means the detection is very reliable. The chance that it's a false positive is low enough that it's not worth your while to audit the rule or to audit the alert, and it's just best to pass it off to a developer saying, this is a true positive, or let's assume this is a true positive, please fix the code.
Right. So it may be that an impact of use is that for some projects, if there's a high automated fixing aspect of the rule, they just fix it and they don't worry about the other portions of the priority or whether or not it is specifically findable or specifically determined whether or not it's a true positive. Whereas they could just choose to not spend time on determining whether or not that particular high automated fixability weakness is actually a problem. They can just fix it.
Precisely.
Okay. So great. So I think that could be really useful. And as we said, the efficiency and the cost of reviewing and auditing all of the alerts and findings that have been found is really high. So this can merge as automated fixing tools in the future are improved. This can help the auditors decide which findings they don't have to worry about or spend much time on. They can just let the tool fix it. Maybe the tools even fix it before it gets to the auditors in some future version.
Right. Theoretically, the technology will be there, even if it's not here today. And while we were obviously thinking of redemption when we did this, the redemption project, there are other automated program repair tools that will come along and maybe perhaps do the job better.
Right. So as a federally funded research and development center, an important aspect of our work here at the Software Engineering Institute is transition. So can we talk about how the outcomes of this research could impact the DoD, the Department of Defense, and other users?
So the main thing is obviously the DoD they first of all have a lot of C code in production and under development, and obviously if they have C code, then they will have lots of alerts from static analysis tools.
Right.
And obviously they could just choose to ignore them. They could choose to not run static analysis tools. And what that means is that the alerts that they don't fix translate to risk. If they put the code in production and that code goes into your tank or your helicopter, that's some risk that's inherent.
Right.
And the DoD doesn't like risk.
Right.
I mean, nobody does.
Right.
So the point is this chops in half or into a third the amount of risk they have to deal with by automating some of the repair and by skipping some of the auditing that they have to do. That, of course, it does require that they use a good static analysis tool and a good repair tool. But again, we're kind of assuming that those will exist. Static analysis is a 40-year-old industry. We have a good idea of how to do it now. And program repair is much younger, but there are good examples of program repair, including but not limited to redemption.
Right. So going back to prioritizing the findings, this is another new way that can help with triaging which findings to address, specifically triaging and identifying which findings can be addressed automatically. And so it should help the efficiency of making much more secure code and reducing risk at a low cost, because you're trying to help them identify which findings can be fixed automatically without much effort.
Mm-hmm. Exactly.
Okay, great. So what upcoming work and updates do you have planned for the secure coding standards?
So we have 2 initiatives going on right now. The smaller of the 2 is just an overhaul of the website, how we host the standards.
Okay.
So they're going to live on GitHub pages, and we're going to accept new comments and suggestions via the existing GitHub pull request system.
Right. So right now it's on a wiki site. Is that correct?
Yes, it's running on the Confluence site we host right now.
So we're converting from a wiki site to a GitHub where people will be able to basically manage the documents as code.
Right.
Okay.
Yes, there'll be GitHub repositories. So if you want to make changes and you're authorized to, you can check out the code and just change it like you change any other GitHub project.
Okay, so not to take too much time on it, can we say a little bit about what is leading that change? Is it to try and, for example, interact with the community in a different way that we think would be more useful for them?
So that lets us be more friendly to people who want to contribute constructively without having as much of the burden of fighting the spammers and other kind of malicious actors on the internet, because GitHub already has infrastructure for that.
Okay, great.
It also allows us to automate some things which are difficult to do. For example, our coding rules have lots of non-compliant code examples. Don't do this at home.
Right.
And compliant solutions. Here, you should do it that way
Right.
instead. But right now, these are all on a wiki. They are hard to test. It's hard for us to make sure that there aren't typos or reasons why these don't actually compile or run properly or behave the way that we say they do.
Right.
So one thing we want to be able to do is automatically scrape them and make them available as test suites.
Right. So instead of the code being part of the documentation, you want to take them out as snippets of code and manage them as code. And so you can automatically test them or use those code snippets for other mechanisms that use code, basically handling it as code instead of documentation.
Right. I mean, one other thing that we could do, I don't think this is going to happen this year, but we could institute a playground whereby when you see a code snippet, there will be a run button which you can click on and see what the code actually does. And surprise, it doesn't do what it was expected to do, but it says what we do. We say, this thing should be printing 1, it's actually printing 2. Click this button to find out.
Right. Okay. What other updates are being planned?
So the more significant update I expect more people will be directly interested in is we're looking at adding more languages that we have coding standards for.
Okay, fantastic.
Right now, our short list is Rust and Python.
Okay.
We're actively in the process of compiling ideas for rules for both of those languages.
Okay, great.
It's a fairly straightforward matter to simply look at, say, the C standard and say which of these rules would still apply to Rust, which ones would still apply to Python, and that's easy to do. But at the SCI, we prefer hard problems because they're hard.
Right, and so Rust and Python are both, going back to that term of memory-safe languages, or if you use them in certain ways, memory-safe. But this will not be our first memory-safe language with standards. We have Java, which also is memory-safe. So
yes.
There are obviously, since we have a standard for Java, more secure coding guidance and weaknesses in the language than just memory safety issues. And so you're going to try and find those and help developers with that in the new languages, it sounds like.
Yes. Java and Python are both memory safe, and Rust is memory safe, but it's not memory safe in the way that Java and Python are.
Okay.
Because Java and Python completely automate away the issue of managing memory. They both use garbage collectors to collect the garbage.
Right. Right.
But Rust does not do that. It simply provides a prover inside the compiler, what they call a borrow checker, which makes sure that with the code that you've written is memory safe, and if you write memory unsafe code, it simply won't compile.
Right, and so as I mentioned earlier, we have blogs and podcasts on the C, C++, and Rust differences in memory safety as well.
To emphasize one of the points Dave was making, a key difference of how Rust works is the kind of mistakes that'll give you a runtime error in Java or Python, they'll get caught at compile time in Rust, so it's one less thing you have to worry about running into for the first time in production.
Right, right.
In theory, you'll get the same performance and low memory usage and low energy or battery usage in Rust that you get in C and C++. You don't have to pay for the excess energy that you would if you use Java or Python.
Right, with its active runtime management. Yep, great. Anything else you want to add?
I think we've hit everything.
Okay.
Yes.
Well, Dave and Joe, thanks again for joining us today. For the audience, we will include links in the transcript to the resources mentioned in the podcast today, including the blog post on the topic. And finally, as a reminder, Our podcasts are available pretty much anywhere you can access podcasts, including SoundCloud, Spotify, Apple Podcasts, as well as the SEI's YouTube channel. If you like what you saw and heard today, please give a thumbs up. Thanks again for joining us.
Thanks for joining us. This episode is available where you download podcasts, including SoundCloud, TuneIn Radio, and Apple Podcasts. It is also available on the SEI website at sei.cmu.edu/podcasts and the SEI's YouTube channel. This copyrighted work is made available through the Software Engineering Institute, a federally funded research and development center sponsored by the U.S. Department of Defense. For more information about the SEI and this work, please visit www.sei.cmu.edu. As always, if you have any questions, please don't hesitate to email us at info@sei.cmu.edu. Thank you.